Thank you very much. First of all, thank you very much to the organizers for putting together such a wonderful workshop. And Timo promised subtropical weather, and this is good. This is a discussion of some paper that Sagar and I put out a little while ago, a few weeks ago. And it's about some aspects of symmetry descent. So it has to do with the SymTFT that was reviewed very nicely by Ling before. So one thing we have learned in the recent past is that it's useful to think of symmetries as topological operators, but it's also very useful to think of any topological operator as a symmetry. So identifying both concepts in quantum field theory has led us to many improvements in our understanding of quantum field theory. And the thing that has been more recent, so that goes back quite a bit, but I think this was made crystal clear in the paper by Gaiotto, Kapustin, Cyber, and Willett almost a decade ago. The thing that's been more recent is that we have learned that this kind of correspondence can be better understood by going one dimension higher and taking some sort of holographic-like perspective. So we construct some topological field theory in one dimension higher, that is, the field theory is in d dimensions. We construct this SymTFT as a topological field theory living in d plus 1 dimensions. And here's some work that explores this concept, and since then there has been many developments. This is clearly a very powerful idea. And Ling already showed pictures like this one. Let me very briefly remind you again of how this works. So say that you have a quantum field theory in d dimensions, and you want to understand the symmetries of this quantum field theory. So it turns out that it's useful to sort of open up the theory as if it was some sort of sandwich and separate the local degrees of freedom, which live in T tilde, from the gap degrees of freedom, which are rho. So you should think of these as the things that you can measure with local experiments, and these things are the things that measure global phenomena, like the difference between SUN and PSUN, and things like that. Connecting these two boundaries is the SymTFT itself, which is a topological field theory that admits different boundary conditions. One boundary condition that the SymTFT admits is this T tilde, the local modes, and the other boundary condition is rho, that tells you about the global form. And one thing I'm omitting here, typically you probably want to put an extra topological theory here for simpler form, an anomaly theory, but for this talk I'm going to omit that subtlety. So yeah, as I said, different choices of rho encode different choices of global forms. You recover the standard topological field theory from these two pieces of data, so the local dynamics and the global form information, basically by closing this sandwich. In this symmetry theory, you will have a bunch of topological operators, and some of them will survive the closing of the sandwich, and some will not. So basically, in this way, we can understand all the topological operators in the quantum field theory from this sort of picture. And the mathematical underpinnings of this sort of analysis were developed very nicely in this paper by Fried, Moore, and Telemann a couple of years ago. All right, so one thing we know since a while ago, and it has been studied in many papers, is that this kind of global phenomena can be understood also from string theory. So here are some early works. There have been many since then. And the thing I will focus on is a proposal that we developed in this couple of papers, particularly in the second one, in which we derive this sort of SymTFT picture from the geometry in cases in which you're doing geometric engineering. So here's the basic cartoon. Say that you have some singularity, 6-dimensional, for example, some Calabi-Yau, and it has a singular point where something interesting happens. You have some field theory living there, and the rest of the geometry is some manifold MD minus 6. So you have a field theory living on this M that's localized on the singularity. And the way that we propose in this paper to read the SymTFT is as follows. Deform this cone into some sort of cigar, integrate along the base of the cigar. That gives you hopefully some sort of interesting topological field theory, and that picture should be identified. So this semi-infinite interval should be identified with this picture here. So the idea here is that the local degrees of freedom still live at the singularity. So this is this bit of the picture. The SymTFT is whatever arises from putting a string theory on B5. So hopefully that gives you interesting topological field theory. And the boundary conditions that you have to specify in a compact setup in quantum gravity, those are given by the choices of rho. Right. So in detail, how did this go? How did we argue that you could do this, at least in some examples? So the basic examples we considered were these cases in which the SymTFT has this form. It has a BF sector. In this case, this is a set n-gauge theory, so this is a way of writing a set n-gauge theory. And you also have some sort of anomaly term, which is of this type. Q here is some number, some rational number that indicates the anomaly of the theory. So this is for some particular example. The details don't matter too much, but the thing I want you to keep in mind is that the SymTFT typically encodes both the symmetry information, which is encoded in this BF term here. Ling already discussed some of this structure, and also the anomaly. So both things are encoded at once in the SymTFT. So how did we argue for this in this original paper? Well, we argue that the BDC term arises from flux non-commutativity, following works by Friedman and Segal and earlier by Moore. And the anomaly term arises from reducing the string theory action. For example, if you're doing M theory, as we were doing some examples here, you can start with the Chern-Simons terms in M theory. So the C3 G4 G4 and C3 X8. You do an actual integration on whatever the base of your cone is, and hopefully that gives you this factor Q that will depend on the geometry of the compactification. Now, of course, this does not fill us with happiness because we are doing two different things for giving terms in the Lagrangian. These are using two different techniques for determining a single object. And at this point, there's two things you can do, basically, well, at least two things. One of them is you can try to understand the BDC term from a dimensional reduction argument, a bit like here. So the unified perspective will be, there will be some sort of string theory action, and I integrate it, and that gives me the action here. Or the other thing you could do is you try to understand anomalies using this sort of flux non-commutativity argument. So this was something I will not discuss, but it has been discussed recently in some beautiful papers. I think this would be a 23, apologies. In some beautiful papers recently. Anyway, I'm going to take a sort of a perspective in which I have some sort of action in a generalized sense. I compactify, and I want to reproduce this thing. Now, why is this difficult? Why can't I just take the M theory action and integrate and obtain this term here? The problem is that in the B wedge DC sector, B comes essentially from the reduction of the electric degrees of freedom, so the C3, and C comes from the magnetic degrees of freedom, so the C6. So if you're trying to dimensionally reduce your 11-dimensional theory, you need to work democratically. Now, including both electric and magnetic degrees of freedom is more or less the same problem as understanding Lagrangian formulation of subdual fields. This is something that's understood, so there are many proposals for solving this, but they're a little bit subtle. I will describe one that we found particularly useful, but presumably there are other ways in which you could solve this problem. Okay, so here's sort of the basic setup. You want to understand this B wedge DC, and in string theory, it comes essentially from some generalized Maxwell theory. So I call generalized Maxwell a free theory of a P-form connection, AP, which has an action like Maxwell, only higher form. This theory has higher symmetries. It has a higher continuous symmetries. It has a U1 P-form symmetry, basically the one that shifts AP. And there's a magnetic one, U1 D minus P minus 2, that shifts the dual photon. So whenever you have Maxwell, free Maxwell, there's a standard argument that allows you to rewrite the theory in terms of the magnetic photon. So the symmetries of the theory are the one that shifts the electric and the one that shifts the magnetic photon. And the thing that we want is a formulation that sees both. In some sense, we want to speak of this theory, but not in terms just of A or just of AD. I want to have both at the same time. All right, so here's the approach we took. It's fairly recent in a way. So it goes back in a way I will explain to Maldacena, Moore, and Cyber, but there was a really nice recent paper by Siet, Tachikawa, and Yonekura, where they give a sort of different perspective on this problem that we found extremely useful. So I will think of generalized Maxwell, the theory I want to construct, as an edge mode of a theory which is Maxwell BF. So what's the Maxwell BF theory? Well, this is a theory in one dimension higher. So now I'm going 2 dimensions higher. my field theory is in d dimensions, the symmetry of T is in d+1, Maxwell BF is in d+2. And it's of the following form. I have first a BF term. So typically we have this B wedge DC, we call this theory a BF theory. And is it possible to move the cursor? No. Maybe. Right. And I can add kinetic terms to B and C. Now, the way to think of these B and C in the Maxwell BF, these are objects that have degree P+1 and D minus P+1. So one good way of thinking of them, and I will solidify this in a second, is as some sort of bulk extension of the field strength and the magnetic field strength. Right, so this is what I have. I have this Maxwell BF theory. If I'm away from the boundary, so somewhere around here, this theory behaves as a massive deformation of BF theory. By that I mean it's still gapped in the air, but there are some massive modes whose mass is controlled by basically these couplings E and M that appear in the kinetic terms, so these couplings here. So they're typically very heavy because I want to make E and M large. And in the strict limit, you end up with pure BF theory. So in the pure BF theory, we know what's going on, right? Let's do BF theory, so let's forget out these couple of terms here and just focus on the BF term itself. The equation of motion for B tells us that DC is 0, and the equation of motion for C tells us that dB is 0, so flat fields. Not much. Now, there's an interesting difference between this Maxwell BF on a space with boundary and pure BF on a space with boundary. And this was pointed out by Shieta, Chikawa, and Yanakura in a very related case in Maxwell-Chern-Simons. Instead of BF theory, they studied Chern-Simons theory. It's basically the same theory. Even a bit more interesting than BF. They pointed out that in this case, in Maxwell-Chern-Simons, you have modes that localize exponentially close to the boundary and describe a self-dual field. And the same statement we argued in the paper is true in Maxwell BF. This is a very minor modification of their argument. So here's the picture. You have some bulk where you effectively have BF theory, and close to the boundary, I'm going to put the boundary at tau equal to 0, and my bulk is at negative taus. So close to the boundary, there's some exponentially growing mode that, as I will show in a second, behaves as a Maxwell field. Importantly, this is a massless Maxwell field. This is the thing that we are after. It's going to be localized exponentially on the boundary. Right, so let's sort of streamline the analysis by choosing an ansatz that will work. So for negative tau, that is going in this direction, I have something which is exponentially localized, so something of this type, and wedge some f, which are functions of the boundary coordinates only. So basically, I'm doing separation of variables. So now you take this ansatz, you put in the equations of motion of Maxwell BF, the classical equations of motion, and what you find is that the classical equations of motion require some things of you. First of all, F and G have to be flat. You also need that alpha is equal to beta, and you also need that F and G are related by Hodge star. Okay? This all follows from the classical equations of motion. Now, if you look at these equations for a second, you'll realize that well, you have already dF equal to 0, and you also have dG equal to 0, but G is a star of F. So you have dF equal to d star of F equal to 0. These are Maxwell's equations of motion in vacuum. So we succeeded in, from a theory that was gapped, reconstructing Maxwell theory on the boundary. The beauty of this approach is that you can see both electric and magnetic degrees of freedom in perfect equality. So you can see both B and C, and there's nothing that forces us to distinguish between one and the other. All right. So we still have to choose boundary conditions. I'm going to choose boundary conditions which are the following type: B equal to C equal to 0 at the boundary, tau equal to 0. So these are sort of Dirichlet boundary conditions. You can choose other values which are still Dirichlet. So for example, B equal to some constant and C equal to some constant. That's okay. That corresponds to coupling generalized Maxwell to background fields for the electric and magnetic degrees of freedom. Something you can do, but we don't need to do this for this talk. So skip that. And the important thing, surprisingly, is that you can impose this Dirichlet boundary condition without killing this space of solutions I just presented. Now, this is perhaps a little bit unintuitive because I'm telling you you have something which is exponentially localized on the boundary, and you're setting b equal to c to 0 in here. Now, what this graph is representing is the curvature of b and the curvature of c. Those are the things that are really localized, the things that are gauge invariant. So I can construct an actual solution for b and c, which behaves in this way. Its curvature is localized close to the boundary, but it goes to 0 at the boundary itself. It is of this form. So if you just put tau equal to 0, it clearly vanishes, so it satisfies this. And you take d of b, assuming that f and g are flat, you end up with something which is localized at the boundary. So same thing as I had before. Right, so this is our basic object. Our b's and c, our solutions of the space, our space of solutions to the equation of motion, classically at least, are going to be of this type. Now, the interesting thing here is that as you go away from the boundary, as you make tau very negative, then this term here will vanish, well, will become irrelevant. So you have that b is equal to f and c is equal to g. And these ones, f and g, we saw before that they had to become flat. We're working locally here. I will introduce non-trivial topology in a second. But at least locally, trivially flat just means that they are pure gauge. So we are saying that on the bulk, as you go to the bulk in this Maxwell BF, your solutions of the equation of motion become pure gauge transformations. So we have an interesting solution. I'm going to draw a picture in a second. Here. We have something which is pure gauge around here. Still pure gauge around here, but more or less constant. And then it sort of glues smoothly to a solution that goes to 0 on the boundary while the curvature doesn't go to 0. Okay. So this is an interesting interpretation of what the Maxwell fields are. So in the boundary, our fields in the quantum field theory, I want you to think of them as gauge parameters for the B and C fields. So my AP and my AD minus P minus 2 are really gauge parameters of these F and G, which are just pure gauge B and C. So the gauge transformations sort of become alive on the boundary by doing this. Okay, so this was sort of the picture that follows from Sieta, Chikawa, and Yonekura. There's a limit that's an interesting limit in which you take E and M to infinity, so to push the mode completely to the boundary. And then here I'm trying to sketch how to think of this limit in a consistent way. So I'm sort of separating the boundary into the region in which the exponential mode has non-trivial curvature, and a region which is still very close to the boundary, but where you can neglect this exponential mode. So I'm sort of approaching the boundary in a scaling limit in which I still keep E and M very large compared to the distance that I'm away from the boundary. So an observer that's sort of looking at the boundary from enough far away, what the observer will see now is a different boundary condition in which the bulk fields are allowed to go to the boundary and become pure gauge. They become pure gauge. So that's because our solution was pure gauge here. I went to 0 on the boundary here in these last slides, but as long as the curvature is negligible, this object is pure gauge. I'm notating that, using this notation, that if B and C are pure gauge, I'm writing that they are in 0 cohomology. Okay, so we can consider this theory in which our fields go to pure gauge on the boundary. It's sort of a weird mix of Dirichlet-Neumann in some sense. If we add a term to the action that lives on the boundary, that forces the pure gauge modes to obey Maxwell dynamics. So this is a term that lives purely in the boundary and it's of this form. As you see, it's manifestly not gauge invariant, but that's okay because our boundary condition B equal to C equal to 0 is also not gauge invariant. We want to give life to the gauge modes, and it better be that these are not gauge invariant. So in fact, this goes back to Maldacena, Moore, and Seiber. When they wanted to understand the singleton mode in some holographic setups, they added precisely this coupling here. Okay, so this was just sort of an analysis of the boundary conditions that you can use to engineer Maxwell from a boundary mode of generalized Maxwell. And the thing to keep in mind is that in the end, what you need to remember is that the Maxwell modes are the gauge transformations. This is not only something which is interesting conceptually, it's going to be very useful in practice for actually doing the computation. Okay, so the idea now is that we go one dimension higher. I want to see the SymTFT as an edge mode. And there are many papers that sort of propose this idea. But I think our approach is at least different conceptually from theirs, although in practice you can obtain many similar results. So the simplest case where you can illustrate this procedure is imagine you take Maxwell theory, so the free Ewing theory, in 4 dimensions, and you put it in a lens space. Now, the lens space doesn't have harmonic 1 cycles or 2 cycles, 1 forms and 2 forms, so there's no massless stuff in the infrared. Wouldn't matter anyway because they're in 1 dimension. But the thing that you do get, or I will argue you get, is a discrete set in quantum mechanics. So Maxwell in an S space is not completely trivial in the IR. It does get some non-trivial quantum mechanics here. So this theory can be described in terms of this BF type theory. Okay, so here's the procedure for how you could analyze this system. We want to understand Maxwell in this space. In our case, L is the lens space, and X is what remains of a space-time, so the space that remains after compactification. And we would like to sort of integrate on L and obtain some sort of BF theory, the one I just described, on X, on the non-compact space. So as I argued, the sort of nice way of thinking of this, or one nice way of thinking of this, is you promote Maxwell to a set of edge modes of BF theory on a theory of 1 dimension higher. I'm going to keep L as it is. I'm going to extend X to 1 dimension higher. And now what you can do is, well, you do gauge transformations in here, you obtain Maxwell theory and integrate, and you get X. The thing you can do, of course, is go the other round. You first integrate on L and then do the gauge transformations. Now, in practice, this route turns out to be much easier. You have BF theory. I mean, much easier. It took us a couple of years. You can do it. Here you have BF theory. You integrate it on L. We know how to do that using some tools I will describe briefly in a second. It gives you another topological field theory in a space with boundaries. You take its transformation of this topological field theory, and you end up with some effective theory that you can show is the BF theory. So that's the approach we took. Okay, so now for actually doing the computation, you need a bit more technology. So far I was working at the level of differential forms, but you need some more powerful formalism. One thing that's powerful enough is the formalism by Hopkins and Singer, which was actually, for the purposes of today, already developed before by Chiggers and Simons, but Hopkins and Singer give a more general perspective on this that works also for K-theory and other generalized commodity theories. Okay, so what's the idea? I want to describe my gauge fields in terms of something they call differential cochains. And a differential cochain is a triple of 3 objects. One of them is an integral cochain. You can think of this as some sort of thinking. Okay. Fine, thank you. So that gives you a sort of local version of the characteristic class of the bundle. Then you have something of degree n minus 1 with real coefficients. This is sort of a local version of the connection on a bundle. And then you have something of degree n, which is a differential form, which you should think of as the curvature of the bundle. So you keep track of these 3 pieces of data, and you call that a differential cochain. And these objects behave very nicely. So you have a differential that sends cochains to cocycles. You have a product, a bit like the cup product, that allows you to multiply cochains. You can integrate. You have an integration behaves as you expect, so it reduces the degree by the dimension of the fiber. You have a Stokes formula. You basically can do all the things that you do with cochains. In this formalism, if you want to describe a U1 bundle with a P-form connection, you do it by describing it as a differential cocycle of degree P plus 1. Gauge transformations, both local and global gauge transformations, are written in this way. You take the differential of some cochain that has the property that its field strength is 0, that's a gauge parameter, and you shift then the cocycle by d of that. Okay, so this is basically all you need to know for this talk of differential cocycles. There's of course much more, but for what I'm going to say, that's enough. And you might wonder why I'm not staying at the level of differential forms, or even at the level of differential characters, which is something that many people in the audience, including myself, were using until recently, much more commonly. Here we really need to work in a bit higher level of refinement, talking about cochains, because in this way we can work locally. So we can describe fields and not just the integral of fields. We don't describe just actions, on a manifold, we actually describe locally what a field is in this way. So we do this without losing any topological data. So this is sort of the best of both worlds. You can keep track of topology, but still think of fields locally, as you would with differential forms. So using these techniques, we can construct the Lagrangian for the same TFT. And why is this useful? Well, remember, I was going 2 dimensions higher. I had my sim TFT that was 1 dimension higher than the field theory, and the field theory lived sort of on the edge of the sim TFT. And I want to think of the sim TFT on the boundary of something else. Now, if I do that, I'm taking the boundary of a boundary, and that makes things much more complicated. I will have to start thinking out corners and so on. If I can work locally, I don't need to worry about that complication. I can stay away from the boundaries. All right. So here's how it goes. Being careful with topology, this is the BF action. And we impose the boundary condition that my fields, my BF fields, are pure gauge. And they stay pure gauge on the boundary. BF theory is not gauge invariant under gauge transformation, so this gives me an effective action on the boundary. For the sim TFT, we're interested in flat connections for technical reasons that I'm happy to explain after the talk. So in this case, the also kinetic term that appeared in the Maldacena, Moore, and Cyber paper is not really relevant for our cases. The boundary term doesn't really play a role here. So if you do a gauge transformation of this type, you will find that the BF action changes by a boundary term. And if you pick these gauge parameters to represent flat backgrounds on the lens space, and you do the integral, something you can do, what you get after short computation is a theory of this type for the gauge transformations. This is a representation in terms of integral cochains of the BF theory that we are after. So this is a simple example with this technology works. Okay, so again, this is the picture. We want to understand this theory, Maxwell theory, as coming from gauge transformation of BF theory, but it's much easier to integrate on L here in this topological theory than in here. Sorry, than in here. But if you think of what we are doing here, this is a version, kind of a weird version of the standard anomaly descent argument. So remember that emphasis before, the sim TFT includes information both about the anomalies and the BF theory. For anomalies, we are used to the idea that if you take the anomaly polynomial, it's exact, it's D of something, D of the Chern-Simons, and that will give you sort of the anomaly terms in the sim TFT. What I'm saying here is different. I'm saying, well, start with some topological theory, the result of this integral, take the gauge variation, and this gives you something exact, which is the sim TFT itself. So this is not quite the standard anomaly descent, but it's sort of reminiscent of it. So far I explained how to do the BF term. You can include couplings by going to more refined formulations. So far it was all our generalized Maxwell. Of course, that's not the most exciting theory in the world, but it's a very rich theory, so that helps us understand some things. But if you want to do string theory, you probably want something like H-twisted K-theory differential cocycles, whatever that means. So if you go and compute the sort of analogous formula in this framework, H-twisted K-theory, you obtain indeed the couplings that I mentioned before, or at least in some cases, where this formulation is appropriate. Okay, so let me finish with some open questions. To me, the sort of 2 main questions are this one and this one. First of all, everything I described so far is applicable to type 1 or type 2, but not so much to M theory, and that's because in M theory I don't know how to describe in a mathematically precise way G4 cubed as a differential cocycle. If anybody knows, I'm more happy to discuss. So M theory is still a bit of an open problem in this approach. One good way of this approach is that it gives you something extremely local, the Lagrangian. So in principle, this should extend to a fully extended topological field theory for the sim TFT. So it will be interesting to redo what we just did in a more categorical way. And something I want to highlight is, well, I started sort of with, there was a forking path. We could do integrate actions, or we could study brain dynamics. Well, now that we understood how to integrate the action, let's study brain dynamics. So some of it is doable, I think, in the abelian case, but there's, I think, a fairly interesting problem, which is how to understand non-abelian stacks. And for that, there was a recent paper by Iñaki, which I think could be illuminating. Thank you.